Welcome. In this session in linear data analysis, we'll briefly explore the statistics of vectors. Specifically, we'll look at the mean and variance of data. So many statistical methods measure samples. So let's suppose that we're given data, and in data analysis, current data analysis, it's quite typical to represent actual data as data vectors and use the symbol X for them. And let's suppose that our data are all real numbers and that there are m of them. So the mean is what you think of the average. So the mean value is, and in statistics, it's typical to write this with an overbar. So that's how we write the mean value. And the mean value is usually defined as we take the sum of all of the values in the data vector and we divide it by the number of data that we have. In data analytics, what we would like to do is we would like to represent this as a vector. So this is a scalar, and the difference vector is something, we'll just temporarily write this as a vector d, and let's suppose that we will say this vector this will be x1 minus its mean value, x2 minus the mean value, and so on until we have written every entry in the original data vector. We would like to gather these, and so what we can do is we can say, well, that's going to be the x vector, and then we'll be subtracting something. And the question is, what are we subtracting? Well, if we think about it, this is a vector that is all ones multiplied by the mean value. So the way I would write that in linear algebra is I would say that's the x mean times the ones vector. Now, if you go calculating things in MATLAB, all you have to do is say d equals x minus mean of x, and MATLAB will say, oh, you're subtracting a scalar from a vector, you must want me to subtract that scalar from every entry, and MATLAB will go ahead and do that. Now, in statistics, they say, we won't use a lot of statistics, but we will use about 3 of their concepts quite often. And we will say that D has m minus 1 degrees of freedom. And we've come across this term, degrees of freedom, and what we mean is distinct values that we need to perform the computation. So let's suppose, for example, we have 2 data vectors, and let's suppose that these are 1, 2, 3, and 4, 5, 6. So what's the mean value of this? Well, that would be 1 plus 2 plus 3 is 6 divided by 3. So the mean value for this is 2. What's the mean value for this? Well, that's 4 plus 5 plus 6 is 15 divided by 3. And so that mean value is 5. So for this, what's the d vector? Well, that would be this value minus 2 is minus 1. This minus 2 is 0. This minus 2 is 1. And what is the mean vector? What's the difference vector for this? Well, that would be 4 minus 5 is minus 1. 5 minus 5 is 0. 6 minus 5 is 1. So what's happened? How is it that 2 data vectors that are distinct, these aren't even scalar multiples of each other, right? These are linearly independent. How is it that two linearly independent vectors have the same difference vector? Well, the answer is this lost degree of freedom. What we've done is we've lost the mean by doing this computation, and by losing the mean, we've lost some information. And that is one of the many concepts that we can use when we try to understand the difference between sample variance and population variance, or sample statistics and population statistics. So of the three concepts in statistics, the first one we'll use is the mean. The next is the variance. And variance is how data vary from the mean. And specifically, it is the mean squared difference. And in mathematics, they will often say that the variance of a data vector is, so this idea is the mean squared difference. So what's the difference? Well, the difference would be xj minus x bar, which we've come across already. So that's the difference. And then what's the squared difference? Well, it's that. And then what's the mean? Well, we have to sum this squared difference for all of the data. So we have to take the sum as j goes from 1 to the number of entries in the data vector. And now we have a choice, and there are two choices, and these are statistically influenced. One is we could divide by the number of entries, or we could divide by the number of degrees of freedom. The MATLAB default, which I'll use, is we divide by the number of degrees of freedom, which is m minus 1. So how could we vectorize this? Well, let's observe that when we have the sum of squares, we came across that already, that's the dot product of a vector with itself. So we could say that another way to write that is, let's keep this 1 over m minus 1 term, is that this sum can now be replaced by, well, what is this sum? Well, that would be this difference the dot product of this difference with itself, which would be this d. So I could represent that as d dot d divided by m minus 1. Let's work through a simple example. Let's suppose that we have x1 equals, and I'll use 1 minus 1, 3. And suppose we have x2 is, I'll use the values 1, 3, 2. So the first thing we do is we form the difference vector. So what is the mean of x1? That would be 1 plus 1 is 0 plus 3 divided by 3, so that would be 1. And the mean of this would be 1 plus 3 is 4 plus 2 is 6 divided by 3, so the mean of that is 2. The difference vector would be x1 minus x1 bar, so that would be d1 equals, that would be 1 minus 1 is 0, minus 1 minus 1 is minus 2, 3 minus 1 is 2. And for our second data vector, the difference vector would be 1 minus 2 is minus 1, 3 minus 2 is 1, 2 minus 2 is 0. So now, how do I calculate the variance? Well, the variance of this would be d1 dot d1. So let's compute that first. So d1 dot d1 equals, that would be 0 plus 2 squared plus 2 squared. So 4 plus 4 is 8. And for this, d2 dot d2 will be 1 plus 1 plus 0 is 2. So now, what is the variance? Well, the variance of x1 is this value divided by m minus 1. So 8 divided by 2 is 4. And the variance of x2 will be 2 divided by 2 is 1. So these are simple examples of how we take data vectors, we find the means, we find the differences, and then we find how the data vary from the mean. So what we would say is that this vector x, I should put a little arrow over that this vector x1 has a higher variance than this vector x2.